Welcome back to the next section in Chapter 3. In this section and the next couple sections, we're going to be dealing with a topic called volumes of rotation or volumes of revolution, solids of revolution, any of those. It all means the same thing. And what that is we're going to take a function and we're going to rotate or revolve it around a an axis, a line, um, and things like that. And it's going to create circles. In this section, the axis that we're revolving it around it'll go all the way up to that. So we're going to be looking at finding, it's called the disk method, because we're going to cut a whole bunch of slices and it's going to make circles. And so we're just going to, and then we're going to integrate over the area of all these circles. So we're going to have pi r squared, and we're going to integrate, and that gets us the volume. In future sections, we'll have washers where it'll be a circle with a chunk cut out of the middle, and so it'll be a circle minus a circle, but we'll get to that in the next section. So there are two types of disks that we use. One of them involves vertical slices. And vertical slices comes from when we revolve it around the x-axis as opposed to the y-axis, or really any horizontal line as opposed to a vertical line. This looks kind of like this. We have a function over here that we're going to revolve around the axis to get a shape that looks like this, and then see how we cut slices vertically to get a whole bunch of circles. In those circles, if we looked at one of the circles, we have the axis right there. The radius is the y value. So that's going to be the radius. We have pi r squared. The radius is the y value. And then the width is dx. So every time we have vertical slices, when we set it up, the volume will equal the integral from a to b, whatever a and b happen to be, of pi r squared, but r is going to be y squared dx. Now we need to have the same variable the whole way through, just like in the previous sections. So this y is going to need to be replaced with the function. So it'll be in terms of x. What does that look like? Let's say we're going to, like this one doesn't actually have numbers, so we'll make one up. Let's say we're going to take the function y equals x squared and rotate it about the x-axis, and we want the volume from x equals 1 to x equals 3. Those are going to be our bounds. And so when we set it up, we'll have the volume equals, the pi can actually come out front because it's a constant. That way it doesn't get in the way inside. We're going to go from 1 to 3 of y. Y is x squared. So we have x squared squared dx. So this step right here, just like before, this is a super important step to show. Even if you are using your calculator to solve the problem, you need to write down, you need to set it up. You have to write that down. For these problems, I recommend doing them by hand, just like the other ones, but these ones specifically because they're generally going to be very doable and it's going to be good practice integrating. Um, I keep saying it, but that practice, that's going to be huge because we don't have a lot of just regular practice integrating. We had it in the last chapter. Um, but other than that, that practice, so you can get better at that skill, is on your own through these problems. And then check your answer with your calculator. So to do this, we have the volume, it's pi from 1 to 3 of x to the 4th dx. Well, to integrate that, we're just going to go up 1, so 5, divide by the new exponent. So that'll be 1/5 x to the 5th from 1 to 3. Don't forget about the pi. That's one of the more common mistakes, by the way, is forgetting that pi. The 1/5 can come out, so we have pi over 5, and then plug in 3 minus plug in 1. 3 to the 5th is 243, minus 1 to the 5th is 1. So the volume equals 242 pi over 5, which, if you're checking it in your calculator or getting a decimal approximation, that's going to be about 152.05 or so. And so, notice the integration, it's the same. If you are doing it in your calculator, like if this is on the AP test, where time is a huge issue, that accuracy, like the AP test is not the time to practice your integration. It's the time to get the problems done correctly, showing what you need to show. If this was AP test, you'd want to show that step, and you'd want to show this. Not necessarily with the middle, just the volume is about equal to 152.05. The stuff in all this stuff in the middle, you don't actually have to show unless it specifically asks for it. But I don't think I have ever seen that. It's always set up the problem and answer. Points for bounds. Honestly, on the AP test, you're probably not going to have a disk. We're going to have a washer like we're going to see in the next section. This is just getting us the basic idea of what we're doing so that we can take that next step in the next section. But you would need to show this step and that step. And so that is for vertical slices. What about horizontal slices? Horizontal slices we're going to revolve around the y-axis or any vertical axis, but today it's specifically the y-axis. When we do that, the radius is now x, and the height is now dy. So when we set up the volume, we'll still have pi integral from a to b x squared dy. We're still going to have to substitute in so that we can have the same variable the whole way through, and that includes the the bounds. Those have to be y variables as well. So if we use the same problem as we did, we had y equals x squared, and then we went from x equals 1 to x equals 3. A quick sketch, by the way, is actually super helpful sometimes. We have y equals x squared. We know that's a parabola. We only really need 1/2 of this because when we revolve it, it's going to be it's going to be symmetric anyway. But we want x equals 1 to 3, which will be y equals 1 to 9, because when x equals 3, y equals 9. And so then we're going to be revolving it this way this time, whereas we went vertically the last time. So in order to solve for things, we know that y equals x squared. That means x equals the square root of y. And then y goes from 1 to 9. A lot of times the bounds will actually be given as y values, but just in case, you can always find them. So setting this up, we're just going to plug them into the equation. Volume equals pi times the integral from 1 to 9 of square root of y squared dy, square root of y squared. That's just y of y dy. We can integrate this. The integral of y, that's going to be 1/2 y squared. So volume, we have pi times 1/2 y squared from 1 to 9. We can plug in the 9 minus plug in the 1. The 1/2 can actually come to the outside. So we'll have pi over 2, 9 squared minus 1 squared. 9 squared is 81, minus 1 squared is 1. That's going to be 80. So this gives us 80 divided by 2 is 40 pi, which is about equal to 125.66. And so notice that that's not the same as it was for the horizontal, because when we do this, the shapes are different depending on the axis we rotate around. But the process is still the same. We set up our equation, plug in to get the variables to be the same, and then integrate. Once again, if you were using a calculator, you would want one of these two steps, and then volume equals 125.66, or volume is about equal to. The approximation isn't usually an issue, but it's usually good to have anyway because it is not an exact value, especially because we have pi. It does equal 40 pi, which you could actually find that too. When you plug it in, if you leave out the pi, this integral will be 40. You can just stick the pi right on top of that, or right onto the end of that. You just have to remember to do it. Remember, forgetting the pi is one of the biggest mistakes people will make in this type of problem. But that is volumes of revolution using disks. Next time, we'll take out a second chunk. Actually a really um, it's a really simple next step to the problem, but we'll take a look at that next time. Until then, keep working problems, keep asking questions, and as always, happy mathing.